All right. Good morning, everyone. How is everyone feeling today? Scared? All right, good. All right, got a wide range. That's fair. The rain had me really bummed out. I miss sunshine, but it's how it is. So, all right. So what are the questions that we want to go over? Do we want to just have a running list and then I'll try to get through all of them? All right. Yeah. Okay. Actually, just shout them out, just whatever numbers. $11, what was that? Oh, T. I'm gonna stop writing 11s. Say it again. Why? You? There were a lot of questions for 11, so it makes sense. There were 26 of them, so. Okay, are these our main ones that we want to focus on? Okay. All right. Well, as we go through them, if you have more questions, we'll do them. All right. So I'm going to just go in order. So I'm going to start with 2. We'll do 2, 4, 6, 9, and then we'll go through our 11s, and then we'll do 12, 13. Okay. So question 2. Hopefully that one is pretty straightforward. So asking what competes with substitution. So remember that when I'm saying compete, I'm talking about the fact that there is multiple reaction pathways that can occur. So what is competing with substitution is our elimination, right? Because if you have hydroxide, you have a strong nucleophile, it could also be a strong base. So that's the situation going on there, is that it's asking, all right, if your reagent is acting as a nucleophile, what else could it act as? It could also act as a base and do the elimination. So addition is going to be the opposite of elimination, because elimination makes pi bonds. Addition is going to use pi bonds, right? So elimination is no pi bond to pi bond. Addition is pi bond to no pi bond. Cyclization is going to occur just whenever, and actually kind of same thing for rearrangement. You can have cycloadditions. You can have substitutions that are cyclizations. So they're not in competition. It's just a descriptor describing the product. So if you make a ring, then it's a cyclization. The rearrangements, they're not in competition with substitution because they can occur alongside our substitutions or eliminations, right? So that's that carbocation rearrangement or the alkyl shift or hydride shift for the carbocation rearrangements. We can have those with SM1 or E1. So it's not in competition, it's just another step within the mechanism. It's just something else to consider. So the only thing that was in competition with substitution was our elimination. Okay, so that does 2. For 4, looking at the major organic product of the following reaction. All right, so we recognize that we have hydrochloric acid and water, and we have our thiol and our alcohol. So first thing that we see is strong acid. You see strong acid, protonate something. So I need to protonate my most basic site in solution. So the question becomes, what is the most basic site in solution? So what is it going to be? The OH. So oxygen is smaller than sulfur. So remember that when we're comparing our elements and they're in the same column on the periodic table, we use size. So the smaller it is, the stronger the base. The larger it is, that was leading to the stronger acid because it was the weaker base. So smaller atom, stronger base. So that tells me oxygen. So we're going to protonate our alcohol, and we're going to get that hydronium ion. Sorry, not hydronium, oxonium ion. Because we have our different, like we don't have any negative charges, also more importantly, this is tertiary, that's reinforcing that we're going to have to make a carbocation, right? We're not going to be able to do like SN2 or any sort of like direct reactions. We're going to have to lose that leaving group, and that's going to give us a carbocation. Here. So then the question becomes, all right, so what is our best nucleophile in solution? Remember that intramolecular is always going to be faster than intermolecular. So we need to look at our substrate, and if I have a potential nucleophile on my molecule, that's the one that reacts. So I see that sulfur. The sulfur is a great nucleophile. So I'm going to count, is it 5 or 6 atoms away? If so, then it's definitely going to be the one that reacts. So I look and I go, all right, so I have 1, 2, 3, 4, 5, 6. Yep, that is 6 atoms away. I'm going to do an intramolecular cyclization. And so then that's what we're seeing for D. That is showing that the sulfur atom was acting as the nucleophile, and it had the oxygen acted as the base. That's why it was the leaving group. So that's why E is wrong. E would be that sulfur was the base and acted as the leaving group, and then oxygen was our nucleophile. But that has the reverse reactivity. Oxygen's the better base, sulfur's the better nucleophile. So that's why E is wrong. And we don't want to make primary leaving groups. So that's, or we don't want to make primary carbocations. So that was the other problem there. The issue with C is that's having our chloride act as the nucleophile. The chloride is, besides the fact that it's intermolecular, meaning that it's a separate molecule coming, and remember, if it's already attached, that's always faster. So this is like separate molecule trying to find the electrophile. Also, remember, chloride is going to be a bad nucleophile in protic solvent because we get the tight solvent shell. So even if like this were the case, oxygen still is a better nucleophile than the chloride, because chloride is not a nucleophile in protic solvent. So that's why C is doubly wrong. It's wrong because it didn't recognize the intramolecular reaction. And it's also wrong because it didn't recognize that chloride is not a good nucleophile in protic solvent. For B, that is triply wrong because it tried to do it twice. So wrong for the same reasons. And then A is incorrect because A is also saying that we're trying to do an SN2 reaction because it's the primary leaving group. But remember that sulfur, that's not going to be like, it's not a strong base. So we're not going to protonate the sulfur first. Also, remember, with sulfur, we always said sulfur wasn't going to be our bases, right? Sulfur went into that nucleophile only category. So sulfur was not going to be a base. So we're not going to protonate that neutral sulfur. So that's why A is incorrect. All right, are there any questions about 4? Cool. All right, let's do 6. All right, so for 6, it's asking us to rank our alcohols in decreasing order reactivity to acid-catalyzed dehydration, which I told you is an E1 reaction, where we're looking at most reactive to least reactive. So acid-catalyzed dehydration just means, hey, we're going to be adding acid, usually it's sulfuric acid, and dehydration, meaning we're going to lose water. So even if I didn't tell you the fact that it's E1, you could still deduce that it's going to have to be an E1 because you're going to have to turn the alcohol into a good leaving group, and you're going to need, the only thing that can happen is form a double bond. Because if that water acts as a nucleophile, it just goes back to the beginning. So we're trying to rank the reactivity. Remember that for our substrates for E1, it is entirely based on the carbocation stability. That's all that matters to our E1 reaction. So we're just looking at what's going to make my most stable carbocations. So we have, for our carbocation stability, we had 2 trends. There was first that getting resonance was the more stabilizing factor. So benzylic was better than allylic, which is better than aliphatic because of resonance, which also answers question 7. So having it right outside the benzene ring is better than having it be right outside the double bond, which is better than having no resonance at all. And then we use the factors that tertiary was better than secondary, which was better than primary. That was due to hyperconjugation and induction. And where most students make the mistake right here is they confuse hyperconjugation and hybridization. Remember, hybridization is mixing. Hybrid, like a hybrid vehicle, uses gasoline and electric. Hybridization is mixing orbitals. So that's not what we're talking about. Hyperconjugation, that's that delocalization of electron density through space. So now we're trying to just say, all right, well, we need to rank these from benzylic, allylic, aliphatic, with tertiary, secondary, primary being our overall ranking. So when I look at this first one, if I imagine that alcohol leaves and I get a carbocation there, this is going to be a primary allylic because it is attached to just one other carbon. That makes it primary, but it's right outside the double bond, so it has resonance. So that makes it allylic. So our next one is going to be secondary allylic. Third in is a secondary benzylic. Fourth in is secondary aliphatic. Fifth is a tertiary aliphatic. And the last one is a primary aliphatic. So I know these 3 are aliphatic because there's no pi bonds. Like there's no double bonds, there's nothing going on there. So there's no resonance possible. So first we consider resonance structures. That means that right away, benzylic, we're doing number 1 is most reactive. So benzylic is number 1. So right outside benzene, you get to be number 1. Then I'm going to look at the ones that are right outside the double bonds. Those get to be my 2 and 3. So I'm going to say this is either 2 or 3, that's either 2 or 3, because it also has resonance. Because they both have resonance, I then move on to the tertiary, secondary, primary ranking, so that secondary is better than primary. Then I move to the structures that have no resonance. So now I'm looking at my aliphatics. So for those, we're going to be looking at the tertiary is just the best out of those, followed by secondary, followed by primary. Any questions about carbocation stabilities? Okay. All right, I'm gonna so number 9 is next. I'm gonna bring my list back down here. Okay. All right, question 9. We are looking at our orbitals. And so we are trying to say, on the structure below here, we want to draw in the necessary molecular orbitals for an E2 reaction. So remember that for E2, it's going to be the base attacks the hydrogen, the beta hydrogen, the hydrogen next door to the leaving group. Then we are going to push the electrons to form the double bond, and we kick out our leaving group. The reason why we have to be antiperiplanar, which is the next part of this, describing why we are antiperiplanar, is because you need this sigma orbital to be parallel to the accessible sigma star, right? So knowing that those are the orbitals that I need, I'm like, okay, well then I need to draw in my sigma orbital and my sigma star for that one. So to know what my sigma and sigma star look like, for that sigma, I am combining an s orbital and an sp3 hybridized orbital, right? Hydrogen only has s orbitals. It doesn't have any p orbitals, right? Because it's row 1. There is no p yet. So for that, it just is s. This carbon has 4 single bonds. So that makes it sp3 hybridized. So it's sp3. So I know that I need to combine a sphere, my s, plus my hybridized orbital, which is the big lobe, little lobe. Because I'm looking at the bonding molecular orbital, the actual sigma, I want the shading to match. So it's going to be compatible shading. So those come together to get that really big side and then just this little backside. So that's what we saw here, the really fat orbital that is going across the carbon and the hydrogen, and then we just have the little one on the backside, because that was the overlap of the s and the sp3 hybridized orbitals. For the sigma star, I am combining my sp3 hybridized carbon with the p orbital of chlorine. So this carbon, again, it has the 4 single bonds, so it is sp3 hybridized. How I know chlorine is when you're looking at the peripheral atoms, you don't hybridize the peripheral atoms. So we're just looking at where does it have an unpaired electron. The unpaired electron is going to be in the p orbital, right? So if you consider its electron configuration, so chlorine has neon, and then, where's chlorine again? 3s2, 3p5. So when I look at that, I'm like, all right, here's my s, there's my p's. You fill singly, and then you pair. The p orbital is where I see the unpaired electron. So that's where I'm making the bond. So I'm going to use that p orbital of the chlorine with the hybridized orbital of my carbon. So that looks like, all right, I'm going to have my hybridized orbital plus my p orbital. So I have a little lobe, big lobe, and then 2 equal sized lobes. And now I need the antibonding orbital for it. So I need the unpaired or the out of phase. So I'm going to shade that one and that one so that now they are mismatched. So that means that they repel each other. So then you're going to get a big outside, little inside, big outside. So that all the electron density is trying to get as far away from each other as possible. And then you just shade every other. And we're just making sure that these are compatible so the electrons can transfer from the sigma into the sigma star. All right, I thought I saw a hand. Does anyone have any questions about how we know that those are the orbitals to draw? Yeah. Mm-hmm. Yeah. So, okay, so why is the s orbital incorporated into every hybridized orbital instead of just using the p orbitals? So the reason why is because, so if I consider something like carbon, I think carbon is easiest to see. I think it's most characteristic. It's the fact that if I take these p orbitals, I'm not seeing this like even distribution of electron density. So you want to try to get to like half full. If you can get, well, actually you want to get full, but if you can get everything half full, then that's more stabilizing. So that's why we sacrifice the s orbital. Yes, the s orbital is more stable and I'm making it less stable. So like that seems weird. Like why am I trying to destabilize what's already happy? And the answer is for the good of the cause, for the good of the atom, because when I excite that up, then all of the electron density lowers into the middle when I get the 4 hybridized orbitals together. So the reason why we're always incorporating this s is because it's going to bring those p's down and it's going to lower the energy of the whole molecule. So that's why you're always adding s into it. Any other questions about our hybridized orbitals or just orbital looks? Okay. So why is antiperiplanar stereochemistry required? So we need antiperiplanar because you need the sigma star to go in, or sorry, the sigma to travel into the sigma star, and the accessible region of the sigma star is 180 degrees on the back side from the leaving group. This was the accessible part of that sigma star. So when I want to break the bond, that's the orbital that I have to attack. Because remember, when I consider my bonding molecular orbitals, where I actually have electron density, I have way more electron density up at the top than I did on the back side. So this is the region where I have the greatest vacancy and opportunity to break the bond. So that's why it's always that antiperiplanar alignment, because that's the accessible region of our sigma star. Cool. All right, any questions about number 9? Okay. All right, let's move into our predict the products. So, alphabet. I think C, no, B comes first. Okay. All right, so looking at structure B, so something to recognize for the predict the products, and this will happen the same way on your exam, is that I am having minimal partial credit. So basically, it doesn't hurt to guess because you'll never go below 0. So guessing isn't a bad thing, but don't try to like hedge your bets and just write a whole bunch of different molecules, because you'll be penalized for each wrong or minor product. So you want to put forward what you're most confident in, and that's what you want to go for. So like this is meant to prevent people from like drawing like the substitution, elimination, oxidate, like instead of just drawing random things, I want you to actually give an educated guess. But I still want you to guess. Like I still want you to answer the question. So that's why I'm saying that each question will not go below 0. So like don't leave anything blank. Like write something. That way you have a chance at some points. Because if it's blank, you have a chance at 0 points because there's nothing written for us to grade. So that's how that grading is working, is you'll never go below 0 for any of the individual parts. But in order to make grading faster, I'm having minimal partial credit, but they're only worth 2 points each, so it's meant to give you the greatest opportunity. So like if you look at this and you're like, I don't know what's going on in B, I'm gonna skip it. It's not that big of a deal because it was only 2 points, right? So that's the idea, is like, I don't want you to spend too much time on any one problem, right? I want you to just like, I'm trying to assess what all do you know from the class. So if there's one thing that you're like, nope, cool, skip it. go to the next. All right, so for B, I see my chromium oxide. So when I see that metal with oxygens, that's going to trigger to me oxidant, right? I see a metal with oxygen, that's going to increase the number of bonds to oxygen. So that was my trigger there, is I'm going to oxidize things. Then I see pyridine. Remember, pyridine is my poison. So that pyridine is going to be, like this reagent is, this combination is PCC. That means that my primary alcohols become aldehydes, and my secondary alcohols become ketones. My tertiary alcohols stay tertiary alcohols. We don't touch those. Tertiary alcohols cannot be oxidized. So the primary alcohol will get oxidized, secondary alcohol will get oxidized, the tertiary alcohol we don't touch. All right, so now we gotta find our alcohols. I see I have this alcohol, this is a primary. I know it's primary because it's only attached to one other carbon. So that primary alcohol is going to become an aldehyde. My secondary alcohol, because it's attached to two other carbons, is going to become a ketone. Everything else just comes along for the ride. So I get benzene that comes in, that doesn't change, we're not gonna touch it. My other carbon scaffold comes together, there's my ketone, and then on the left-hand side, I get my aldehyde, whether you show the bonds going up or down, whatever, it doesn't matter. Whether you show the hydrogen or leave it implicit, doesn't matter. As long as you show carbonyl, carbonyl, that gets you full credit. Yes? Yes, so when you look at the instructions on the front page, and actually for you, I had to put it on the next page, so it'll be right here. But yeah, we're assuming all reagents are in excess. Yeah. All right, any other questions about B? Okay. Oops. Oh, that was 12B. Zoops. Well, we did B anyway. My bad. So C did come first. All right, looking at C. All right, so I see sodium iodide, tert-butanol, and a triflate. So I'm seeing that I have this secondary leaving group with a strong nucleophile, only, and a protic solvent. Iodide is so large that it does not form a solvent shell. So iodide is still my best nucleophile in solution, right? The tert-butanol is not going to be my nucleophile. The iodine is still my nucleophile. So when I do nucleophile only, that tells me SN2 or SN1. Secondary leaving group, still SN2 or SN1. Protic solvent, that's what tells me SN1. So then I need to do an SN1 reaction, and I'm going to have iodine still as my best nucleophile. So I'm going to have leaving group leaves. I get a carbocation. Iodine attacks. And I get iodine incorporated. I lose stereochemistry because of the fact that I went through a carbocation intermediate. So you can either show, also it's not a chiral center, but whatever. If you showed the wedges and dashes, you had to show both in order to get full credit, or actually in order to get any credit. You needed to indicate to me that you knew it was SN1. That's what I was looking for, is did you know you were doing SN1? Cool. So either you needed to show both, or you had to show the straight line showing that you recognize that you would lose your stereochemistry. I think that's how I graded it. Yeah. Yeah, so you didn't get partial credit for drawing just one of them in, because that didn't indicate to me that you knew it was SN1. All right. Any questions about C? Yes? You got to show me the products. I need to see that you know how to apply it. Any other questions? Okay. All right, so we did C. Oh gosh. E, I think that's next. Oh my God, I gotta move this 12 out of my way. I think E is next. All right. So for E, I see that I have two potential leaving groups. Well, really, I only have one because remember, fluoride, never a leaving group. So really, bromine's my only leaving group. But if you are comparing both the fluorine and the bromine, because you saw two halogens and you were like, I don't know, the larger atom is going to be the better leaving group. So also, we just always remember fluoride is way too reactive. It is never stable as a leaving group. Fluorine, never a leaving group. That amine is going to be both a good nucleophile and good base. That was something special about our nitrogens, was that our nitrogen had this unique reactivity. So nitrogens, I want you to think amine base. That's what I want you to think. Like ammonia, we typically use it as a base. There's something special about ammonia specifically, that NH3, because it's so small, it is also a good nucleophile. So once you start building out larger amines, you start putting carbons on it, they become less good nucleophiles. So this is specifically to ammonia. Ammonia is uniquely a good nucleophile. So because of this competitive reactivity, and also because in one of my problem sets, I only used it as a base. In the textbook, it uses only as a nucleophile, and that was confusing. So for this question, I allowed both the SN2 and the E2 product. Because if you did that association that I want you to do, where you see nitrogen and you think base, then cool, you did E2. Because I wanted you to relate it to the other amines that we saw. So like I gave you like triethylamine, diisopropylamine. I gave you other amines, and I had you do E2 with them. I had you use them as bases. So if you did that, sweet. But because the textbook is saying that this is something unique about ammonia, which is true, then if you used it for SN2, cool. That also worked. So if I do SN2, then my amine does the backside attack and it comes in. So there are two ways you could show this. Either show that your nitrogen is now on the left-hand side. So you switch your lines. So your leaving group is on the right, so your nucleophile goes on the left, and you keep the wedges and dashes the same. Or what I prefer to do is I have my nucleophile directly replace my leaving group. I just swap it out, like I just erase my leaving group, I put in my nucleophile, and then I just flip my wedges and dashes. So that way I know that I did my version of stereochemistry. You don't do both because then that's retention. So you either need to show that your nucleophile is now on the left side, or change your wedge to a dash to indicate that you did inversion of stereochemistry. You could also assign R and S to double check yourself because, nope, that doesn't help you because they're not the same level of priority. I wouldn't assign R and S here because I think they're actually both S. Yeah, just recognize that you need to either do the dash or change the actual left and right side of it. So that's if you did SN2. If you did E2, then we're looking at you want to take the anti-periplanar hydrogen. There's only one beta hydrogen because there's only one other carbon. So it has to be one of the hydrogens off this side. So if you use ammonia to take that proton to do the E2, then you get your, I kept the fluorine on the top. It doesn't matter. you could draw the fluorine down here. Doesn't matter how you rotate it. It's the fact that bromine was the one that was lost. That's the significant thing. Right? So either answer for this question receive full credit. Yeah. Any questions about that? Yes. Right. So for this particular case, specifically because it's ammonia, which is a weird thing, specifically for ammonia, it actually is slightly better as a nucleophile. So technically your SN2 would be major, but that's weird. If you take any other amine, it would be the elimination. So like that's just a weird exception that I didn't mean to accidentally pick. Okay. All right. We did E. J? Well, we'll do J and K, I think are the next ones. All right. Looking at J. So we have our sodium borodeuteride. Don't get freaked out by Ds. That D is deuterium. Right? Deuterium is not a new element. If you look on the periodic table, there is no D just by itself. There are the letter Ds, but like there is no just capital D on the periodic table. So that isn't a new element. That is that isotope of hydrogen. It's heavy hydrogen. Also, if you're looking at it, this thing looks like NaBH4, right? So it's going to act like sodium borohydride. It's just the reason I'm using deuterium here is because I want to make sure that you know where that hydrogen went. So I want you to indicate to me that you know exactly where those elements ended up in the molecule. And then here, I was, I guess, kind, I don't know. I gave you a deuterated solvent as well to make sure that you recognize that this is going to be what ends up on the oxygen. This is what ends up on the carbon. So now we also need to remember our reactivity. Sodium borohydride can only reduce aldehydes, ketones, and acid halides. It doesn't work for our other higher oxidation states. It doesn't work for the ester, it doesn't work for carboxylic acid. It can't reduce those. So our sodium borohydride is only going to work for your aldehydes, ketones, and acid halides. It turns those into alcohols. Those are the only starting materials that work. So when I look at this, I see that I have an ester on the left side and a ketone on the right side. I'm not going to touch the ester. The ester does not get reduced. It is not electrophilic enough for that sodium borohydride or sodium borodeuteride. The sodium borodeuteride is not our stronger reductant. The stronger reductant is lithium aluminum hydride. LAH reduces everything. If you want to change every carbonyl into just an alcohol, LAH is the reagent you want. Lithium aluminum hydride reacts with every carbonyl. Sodium borohydride is selective. It does aldehydes, ketones, and acid halides. That's it. So that means I'm going to redraw my ester. That stays put. And then I'm going to have, for the ketone, it will become an alcohol, but it's a deuterated alcohol. So that this deuterium, that came from the solvent, and then the deuterium on the carbon is the one that came from the reductant. Because we have that added in, and we do that addition reaction. So that you take the electrons, it attacks the carbon of the carbonyl, electrons go up onto oxygen, and then we protonate that O- with our solvent. Right? Any, yes? Mm-hmm. Yeah, so if we had LAH, that lithium aluminum hydride, So first of all, you would need it to be 2 steps, and you would need some sort of aprotic solvent, and then the second step, you would do your acid workup. You would turn both into alcohols. So you're just gonna like delete everything else. You take alcohol, or the carbonyl becomes the alcohol, and then the other side also becomes an alcohol. So you get OH, OH. Or if this was deuterium, or here, I'll just label these red H's to show where they went. So if it was deuterium, everywhere where you see the red H, you would write a D. And then for your HCl, that would be what ends up on the oxygen, right? That's what protonates it. So if this was DCl and D2O, then you would end up with deuteriums on your oxygens, right? Because the question here is, do you recognize where each element went? What is the role of each individual reagent? That's the point of that question. Cool. All right. Any other questions about J? All right. K. All right, looking at K, I see TFCl. So if you recognize this reagent, then that's going to be a lot better for you. If you don't, then hopefully you see chlorine and see that chlorine is a leaving group. So that would be my hope. So triple chloride is this thing, right? It's one of it makes the sulfonates. So when we see that reagent, that's going to turn it into our alcohols into good leaving groups. That's the point of that reagent. So our MSCl, TSCl, or TFCl, all it's doing is changing this side. So it's either a CF3, a CH3, or a toluene, so benzene with a CH3. And that's all that's doing, is it's going to turn my alcohol into a good leaving group. Now remember that inversion of stereochemistry only occurs at the electrophile. So this carbon is not involved in the mechanism. This carbon is coming along for the ride. When we do our arrows, it's the oxygen attacks the sulfur and kicks out the chlorine. The rest of the molecule came along for the ride so that we would get our wedged OH. You get your TF there. I don't want to draw the whole thing. I'm just going to abbreviate to TF. And you would have this protonated intermediate. The role of your base, which I should have indicated that it was 1 equivalent, but remember, it's acid-base chemistry happens fast. That happens first. So the base is just going to deprotonate in order to get it neutral. So it was just hoping that you would recognize that those were the conditions to turn this into a good leaving group. Cool. Any questions about that one? So no one actually drew this because I had my TAs double check over the summer, although I guess they could have made a mistake. So to my knowledge, nobody drew this. But theoretically, because I told you to assume all reagents are in excess, so if this was in excess, then that would have been a base only, indicating that we're doing E2. It's also a bulky base, indicating that we're going to do the Hoffman. So it should have, if you drew this product, that would have also been accepted. Although I don't think that ended up on the answer key because I don't think anyone drew it. But technically, if it's in excess, then it could have done the E2. Yes? Right, so the reason it stays the wedge is because this is my nucleophile. So the fact that this is the nucleophile, I don't have any arrows touching that carbon. So if no arrows touch that carbon, I don't touch that carbon either. There is nothing to invert that stereochemistry. We only invert the stereochemistry of the electrophile, not the nucleophile. So this wedged alcohol stays a wedged leaving group. Any other questions about K? All right, so we did J, we did K. All right, we're getting to, that's a Z. We did K. So we have W, T, U, S, Y, Z. Okay. S is next. All right, we have S, T, W, Y, Z. All right. For this one, I see OH minus. O minus, that's my strong nucleophile, strong base. That tells me SN2 or E2. I then look at my leaving group. That's a secondary leaving group. That doesn't help me. That is either SN2 or E2. So then I look at temperature, not solvent, because solvent doesn't help me. So I look at my temperature. I see heat. Heat tells me E2. So I need to do E2 elimination. My regioselectivity that I'm going to consider is that this is a non-bulky base. That tells me I'm going to do my Zatsev alkene, meaning I need to take the hydrogen off the right-hand side, right? Because I have beta hydrogens here and here. There are 3 here, 1 here. I'm going to take the one from the more substituted side because it's going to lead to the more stable alkene, and that OH is small, so it can get there. My stereochemistry that I'm going to consider is I only have 1 beta hydrogen on that side. So I either need to check my Newman or I need to just rotate because it must be antiperiplanar. Right? If it doesn't go antiperiplanar, it cannot happen. You cannot do an E2 without it being antiperiplanar. You just can't make the product. So I don't feel like drawing a Newman projection, so I'm just going to rotate this to get my hydrogen to be onto the dash. So when I look at this, so all I did was I drew in my wedges and dashes that are just blanks here. So I want my hydrogen to go to the dash. So wedge goes to dash, which actually I'm going to keep these consistent because I drew my wedge on the right-hand side. It doesn't matter. It's totally whatever. I'm just trying to illustrate like general location. So the H went over to the dash. So then the dash goes to the line. My line goes to the wedge. And I don't know why I have a combination of every form of abbreviation on this structure, but whatever. So, and if you mix like abbreviations where you do line diagrams or you write CH3 or you use your abbreviation of like ME or ET, as long as you do it correctly, then you're fine. You can use any abbreviation you want. You could draw actual line diagrams, you could use the abbreviations. As long as you're correct, I don't care. So whichever abbreviation's your favorite, you can stick with that, or you can do as I did, like with this weird hodgepodge of just all of them. Cool, whatever. So what this is indicating to me is that when I draw this double bond in, I'm going to get my methyls on opposite side. My ethyl is going to be on the same side as the methyl. So then that's going to be my product. So it's OH minus, comes in, takes that hydrogen, you make your double bond, and you kick out your leaving group. But the trick here, the challenge here, wasn't a trick. The challenge here was to make sure you recognize that it had to be antiperiplanar. Cool. So that made the Z alkene. Because remember, E2 could do E or Z. It prefers E if it has a choice. But if it doesn't have a choice, it's got to do antiperiplanar, right? So 1 beta hydrogen means that it could be E or Z. We had to check the Newman to know. If there are multiple beta hydrogens, make the most stable alkene. If it gets a choice, always make the most stable alkene. Get the big groups as far apart as possible. All right, any questions about S? Yes. If you drew it as E, no, you would not get half credit. Yep. So then that was because that's the point of that question. So that's what I mean by like why it's the minimal partial credit, is because each question is trying to get at one specific thing. Did you recognize that this one had to be antiperiplanar? So like I have other structures where the stereochemistry didn't matter, and so then you would get that because I just wanted to see, did you know to do E2? So then those questions you would have gotten the points. But this one, because I'm specifically looking at, did you know that with this E2, you had to get the Z alkene? That's what I was looking for. Cool. Okay. All right, for T, I see strong acid. Strong acid protonates something. My most basic site is that oxygen. So I'm going to take this oxygen. It's going to take that proton. It gets protonated. All right, try to make it an actual 5-membered ring. That looks weird, but whatever. Let me make it a little bit prettier. And actually finish it. There we go. All right, so at this point, I now have my good leaving group. Bromide is a good nucleophile. And I see that I have, so this is nucleophile only. So that's SN2 or SN1. I see that I have a tertiary side. And with that positive charges, remember with acids, acids prefer SN1, right? This is an ether, so my hope was that you would recognize it like with ethers and epoxides, they all do that same thing. So that we're recognizing that we have that strong acid. So we're going to form the tertiary carbocation. Once you make the tertiary carbocation, you lose stereochemistry. And once you lose that stereochemistry, you lose the wedges and dashes. And now the bromide can attack. Any questions about that? Okay. W. All right, we're again seeing our sodium iodide with terbutanol. So we've already deduced that iodine is going to be my nucleophile. So I see that this is a tertiary leaving group. That tells me SN1. Iodine told me SN2 or SN1. I'm only doing substitution. I see the tertiary leaving group. That immediately tells me SN1, and that I don't even need to look at the solvent. That doesn't matter. So I'm just going to do SN1. So I'm going to have leaving group leaves. I'm going to abbreviate this as pH. This benzene is just pH to save space. And again, you can do that as well. And then at this point, the point of this question was recognizing that benzylic is going to be more stable than even a tertiary aliphatic. Getting resonance makes you more stable. So the point of this question was recognizing that you needed to do that hydride shift in order to get the resonance stabilized carbocation that iodine then attacks. And again, because you get those carbocations, you have lost the stereochemistry, so you just do all straight lines on any time you saw the carbocation. Cool. Any questions about W? All right. For Y, oh, this basically, we already did this one, because that was a question of like, what do you do with LAH? It reduces every carbonyl. So this becomes OH, this becomes OH, and you lose everything else. LAH reduces every single carbonyl. It is not selective. It is, the technical term is promiscuous. It reacts with everything. Well, every carbonyl. Yeah. Yeah. Yeah, so remember that this is tertiary aliphatic. This is secondary benzylic. Resonance makes it more stable. Yeah, so yeah, maybe I shouldn't have abbreviated the pH. I have benzene here. So it's the fact that it's right next to the benzene ring, it has resonance. So yeah, it's secondary, but it's secondary benzylic. And that's always gonna be more stable. Ooh, look at the time. Okay. Yeah. This one I actually did in lecture last class. So hope that helps. And yeah, if you have any other questions, I can try to answer them quickly. And then I do have office hours, so if you're able to come to office hours, I'll do the rest of them. Hey, what's up?